All right, so we're going to wrap up this integration by parts section. We have two examples to go over, but they're going to be, at least this first one, is going to be kind of lengthy. So let's get our pencils ready. We're going to also verify this on the calculator, so if you have one available, it might not be a bad idea to get it out. So we have some function x cubed times cosine 2x. They're asking us to find the average value, the average answer, the average output of this function on the interval from 0 to pi over 2. So how can we calculate average value? There's a difference between average value and average rate of change. Similar wording, two different, completely different concepts. Yeah?
Find the integral of that
Divided by pi over 2. Okay, so we have, Eric gave it to us kind of in a nutshell, but the general formula or kind of setup of average value, we have 1 over b minus a. B and a come from your interval, so we'd have pi over 2 minus 0, which would just be pi over 2. And then we're going to integrate the function. All right, I'm going to clean this up a bit. Instead of having 1 over pi over 2, instead of dividing by that fraction, you can multiply by the reciprocal. All right, so at this point, I want you to go ahead and type this into your calculator to see what you would get as your average value. And then we're going to try to get the same answer by hand. Try. Right, keyword there. Okay, so let your calculator do the work at first, and then we'll try to verify it by hand. Make sure you're in radian mode because we have trig. Can we get it? Negative 0.70063, something like that. About right? Okay, so we're going to try to get the same answer by hand. Okay, maybe in an exact terms because that's kind of a rounded decimal. Let's not lose sight that this is our goal that we're trying to calculate. Okay, so maybe let's just focus on the integral portion first, and then once we have that integral value, we'll simply multiply by 2 over pi. So instead of using this 2 over pi through our integration process, we'll just bring it in at the end. Okay, so let's just focus on the integral from 0 to pi over 2 of this f of x function. So how might you want to work backwards? Think about your integration techniques. Reverse power rule, u substitution. We've been talking about by parts. We did a little bit of partial fractions in the last unit. We're going to do more of that in this unit too. Anything you feel like doing? Go ahead. Let's do by parts. Okay, so we should be easily able to take the derivative of one, at least one, and then integrate the other, or maybe both. If we're going to use by parts, let's think about our acronym, anagram, I never remember. Yeah.
We're going to use like cosine 2x right for dv.
Okay, so that's our trig function, which means the algebraic of x cubed would be our u. Okay, so think about detail. So we got to work backwards from dv to get v, and differentiate, find the derivative of u to get du. Can we work backwards from cosine of 2x? Yeah. Sine of 2x over 2, yep, or you can bring that over 2 out front as a coefficient of 1/2, either one. Good. All right, so now that we have all four parts or pieces, how do we bring those pieces together using our by parts kind of formula? Do you remember which ones we got, Eric?
U times v minus the integral from 0 to pi to
v du. Okay, so we need u times v. So order doesn't matter when you're multiplying. You can rearrange it however you want. Minus the integral from 0 to pi over 2, if you want to go ahead and write that in there, of v du. We have to multiply the dx over, but I think we can do that. So if we did v du, that would be 3/2 x squared sine of 2x dx. So in solving this original integral we had that was supposed to represent the average value, we just didn't write the pi or 2 over pi out front. We should be able to integrate this new integral more easily. Should. Okay? So take a look at your new integral. How do you want to work backwards from that? Think about your techniques. Yeah. We're going to do by parts again. All right. I think we saw one like this last time we were together, where we had to do it multiple times. So think about detail. Maybe we'll let the trig be the dv, and the other pieces, the algebraic, be u.
Are we able to move it through so as well as the coefficient in front of the integral?
In front of what?
The integral?
Yes. If you wanted to move it out there, that's fine. But you would have to eventually distribute it in. Okay? So it's completely up to you as long as you keep the algebra organized. Okay? If we work backwards from dv, we'd have a negative 1/2 cosine of 2x, and du over dx, we would have 3x. All right, so let's go ahead and rewrite kind of what we have here, keeping everything organized so we don't lose track of any pieces. We have the u times v from the initial by parts that we did, and we have to subtract whatever the by parts setup gives us from this new integral. So we're going to subtract all those pieces. So using our new by parts, we need u times v. So we'd have a negative 3/4 x squared cosine of 2x minus the integral of v du. So negative 3/2 x cosine of 2x dx. We're doing okay so far? Okay. Maybe let's go ahead and distribute in that subtraction to get rid of those brackets. Let's try this. So if I distribute in the negative into the integral, that would change to a positive. We could factor out or pull out the -3/2 as the coefficient, but maybe we'll just pull out the negative and keep the 3/2 in there. Doesn't matter what you would do, it'll all work out in the end as long as you keep your algebra organized. So apparently this new integral should be easier than the other ones we did. What do you want to try for this one? Can we easily figure it out, or do we have to use some type of technique? Caitlin sees it. What are we going to do? And we're going to do by parts again. Alright, so we have the trig in there. And the algebraic. So backwards from our trig, we'll have 1/2 sine of 2x. Derivative of u, we'll have 3/2. Alright, so let's keep it all organized. Bring down the original u times v from the first by parts. We'll bring down the next u times v from the second by parts we did. And we need to subtract the integral, which we are doing by parts a third time. So we have to make sure we subtract all of those pieces from the by parts process. So let's see, we have u times v, 3/4 x sine of 2x, minus the integral of v du, 3/4 sine of 2x dx. Alright, let's check out our new integral. Maybe we can distribute in that minus sign. Change it to a plus. So our new integral should be easier than all the other ones we've been doing. Can we go backwards from that one pretty simply? Yeah? What are we going to get? Actually, I think this would end up being a minus. Let's see, we'd have a 3/8 cosine of 2x. We agree with that? Is that okay? Alright, and we still have all of this other u times v from the 3 by parts that we had to do. Alright, so we officially found the antiderivative. Let's not lose sight that we need to still evaluate this from pi over 2, from 0 rather, to pi over 2. Alright, so top bound minus bottom bound. We got to plug in pi over 2 first. In our first term here, if we plug pi over 2 into the trig function sine, it would become a pi. Sine of pi is 0. So it really doesn't matter what else we get from the 1/2 x to the third. Okay, so this first term is 0. If we plug in pi over 2 into our next term, we'd have cosine of pi, which is a -1. So we would need a -1 times a 3/4, which would be a -3/4, times pi over 2 squared, which would be pi squared over 4. So in the end, we'd have 3 pi squared over 16. Alright, if we plug pi over 2 into the next term, we'd have sine of pi again, which is 0. So that whole term goes away. And if we plug in pi over 2 into our last term, we'd have cosine of pi, which is -1, times a -3/8 would change to a positive. So that's if we plug in pi over 2. We now have to subtract what we get when we plug in the bottom bound. This one's going to be nice. If we plug in 0 for the x's, x cubed is still 0, so that whole term would go away. X squared is still 0, so that whole term's going to go away. X to the first is still 0, so that whole term's gone. And last but not least, cosine of 0 is 1, so it'd be left with the -3/8. Okay, so we have -3 pi squared over 16 plus 3/8 plus another 3/8. Let's see, if we get a common denominator, multiplying the last two fractions by 2 on top and bottom, we'd have a -3 pi squared plus 6 plus another 6, so that would give us 12 all over 16. Are we doing okay, calculation-wise? Okay, so this is the value of the integral, not necessarily the average value we found on the calculator. Remember at the very top, we were just analyzing the integral itself. We still have to remember, let's not forget that we have that 1 over b minus a out front. Okay, so this value of the integral, we're going to multiply by that 2 over pi. So what we did, hopefully, I'm hoping this is going to check out, is that this is the exact average value. No decimals, anything like that, no rounding, okay? Let's go ahead and try to type this in on our calculator, and hopefully, crossing our fingers, it matches the -0.70063. It does. Okay. I always get nervous when it's time to go over those because there's so many places that can steer you wrong, you know.
The first time I plugged in my calculator, I plugged it in wrong.
Uh-huh.
And then I was like, crap, we did the same thing, and then I realized it.
What you did. Should work out. We doing okay? We didn't forget by parts yet? I know it's been a while. Alright. We're going to check out one more example. Not as involved as that one, I promise. Alright, so we're going to evaluate that integral. Now, initially, when you look at this, it doesn't fit the reverse power rule because we don't have any polynomials. We can't really do u substitution because if you let u be e to the x, we don't have another e to the x in there to cancel it out. And if you let u be secant x, the derivative of secant x is not showing up somewhere else in the integral that would easily cancel out the x's. So reverse power rule is gone, u substitution is gone. That means we're left with either by parts or some type of partial fraction. Now when we did partial fractions very briefly, you had to be able to factor the denominator. And clearly that's not the case here. So the only other option we have is by parts, but this is not representing the by parts kind of setup. Yeah.
So we can just rewrite it as secant inverse of x.
We're going to rewrite it, okay? Because by parts is always multiplying two different functions together. And in this case, we're dividing two functions, but you can easily turn division into multiplication. So Caitlin, how might you want to rewrite this?
E to the x times secant x to the negative first. Wouldn't that just be secant inverse of x, or is that different?
There's a difference. Okay, so secant x to the negative first is not the same as secant inverse. Okay? If you were to bring secant up from the bottom of a fraction, it actually changes a trig function. For instance, you can think about this as e to the x over, instead of secant, can you rewrite that as another trig function? Secant is 1 over cosine, okay? So instead of dividing by 1 over cosine, you can bring that up and multiply by the reciprocal, which would just be cosine. Okay, so instead of dividing two different functions together, we can rewrite them as multiplying two different functions together. All right, so looking at this, what do you want to let dv be? And what about u? Think about detail. Yeah.
dv is dx.
Uh-huh.
And u is cosine.
Cosine of x. There we go. All right, so backwards from e to the x, we would just have e to the x. And then derivative of cosine, we have negative sine. Okay, so this original integral we had is exactly the same, aka equal, to our by parts setup. We need u times v, any order is fine, minus the integral of v du. All right, we have a double negative showing up in there, so if you want to pull the negative out of the integral, it would change it to a plus. So supposedly this new integral we have should be easier to figure out than the previous one. So think about some techniques. What do you want to try? Go ahead, Caitlin. By parts again. All right, so detail, we have that exponential in there. So backwards from e to the x is e to the x, and derivative of sine is cosine. So let's not lose sight of what we've had so far. We have the original u times v from the first by parts, yeah.
I was going to say, so it's just going to keep the problem back and forth.
Let's take a look at that.
So,
Uh-huh.
can't we use, there's another theorem, right, where we can,
I don't know about another theorem, but there is something tricky that we're going to do. Okay? So do you notice how the new integral we had is technically, not even technically, exactly the same as the first one we did? Okay? So if we were to go through by parts again, we would just keep generating the same results over and over and over. We're going to be stuck in an endless loop. So there must be some way for us to kind of get out of that. So here's what's going to be a little tricky. Bless you. We know on this side of the equal sign was the original integral we had. Right? Can we add this new integral we have to the other side? Aren't they like terms? Aren't they the exact same integral? So if we add that integral over, we would essentially have two of them on that side. Okay, so maybe let's take note of that. This new integral we had here, we'll say matches the original. Okay. So we would be stuck in that endless cycle. if you notice that, okay, if you end up with an integral that matches the original, you can move it to the other side because it's technically a like term. All right, so if our goal for this question was to figure out what's the integral of e to the x cosine of x, where can we go from there? If our goal is to figure out this little clouded section, what do you want to do, Eric? We're going to divide the 2 over. So e to the x cosine x plus e to the x sine x all over 2. So the original integral we were trying to evaluate, work backwards from, we have that solution. I guess technically we don't know our bounds, so a plus c needs to be in there too. Okay, but that one's a little tricky because notice how we would have been in that endless loop, and if that happens you're thinking, oh my gosh, this is just going to keep going. But you can add over that, or subtract over, whatever the case is, that integral. Do we see that? Alright, so that's it for by parts.
Please excuse the interruption. Would all students that attended the boys soccer match last night against Burrell please report to the auditorium? Thanks.
Alright. Good timing. Alright, we're done with by parts. Go ahead and work on some of the homework problems if you haven't already. Tomorrow I'll probably give you as a homework day as well.
People were what? Oh. They were like, oh wait. Oh, they were saying, oh, that's ridiculous. That's what